So homework 2 is out now. I recognize that there's a really broad spectrum of background in terms of whether people have seen deep learning or not before, or taken a class or used it extensively. Just a quick handle, which of you have used TensorFlow or PyTorch before? A number of you, but not everybody. So what we're going to be doing this week in sessions is we're going to be having some more background on deep learning. You're not expected to become or to be a deep learning expert to be in this class, but you will need to have some basic skills in order to do homework 2 and be able to use function approximation with a deep neural network. So I encourage you to go to session this week if you don't have a background on that. We're going to today cover a little bit on deep learning, but very, very, very small amount, and focus more on deep reinforcement learning. But the sessions will be a good chance to catch up on that material. We're also going to be releasing by the end of tomorrow what the default project will be for this class. And you guys will get to pick whether or not you want to do your own constructed project or the default project. And those proposals will be due fairly soon, in a little over a week. Are there any other questions that people have right now? Yeah.
The assignment's not limited to TensorFlow?
So the question, if the assignment is limited to TensorFlow, I'm pretty sure that everything relies that you're using TensorFlow. So yeah, just feel free to reach out on Piazza to double check that, but I'm pretty sure all of our auto graders are set up for TensorFlow. So for this one, even if you use PyTorch normally, please use TensorFlow. All of you guys also should have access to the Azure credit. If you have any questions about getting set up with that, feel free to use the Piazza channel. We also released a tutorial for how to just sort of set up your machine last week. So if you're having any questions with that, that's a great place to get started. You can look at the tutorial, or you can look at the video, or you can reach out to us on Piazza. Any other questions? All right, so we're going to go ahead and get started. What we're going to be covering today is sort of a very brief overview about deep learning, as well as deep Q learning. So in terms of where we're in the class, we've been discussing how to learn to make decisions in the world when we don't know the dynamics model or the reward model in advance. And last week we were discussing value function approximation, particularly linear value function approximation. And today we're going to start to talk about other forms of value function approximation, in particular using deep neural networks. So why did we want to do this at all? Well, the reasons we wanted to start thinking about using function approximators is that if we want to be able to use reinforcement learning to tackle really complex, hairy problems, we need to be able to deal with the fact that often we're going to have very high dimensional input signals or observations. So we want to be able to deal with sort of pixel input like images, or we want to be able to deal with really complex information about customers or patients or students, where we might have enormous state and or action spaces. I'll note today that we're mostly not going to talk so much about enormous action spaces, but we are going to think a lot about really large state spaces. And so when we started talking about those, I was arguing that we either need representations of models. Those mean the sort of the dynamics or the reward models, T or R, or our state action values Q or V, or our policies that can generalize across states and our actions, with the idea being that we may in fact never encounter the exact same state again. You might never see the exact same image of the world again, but we want to be able to generalize from our past experience. And so we thought about, instead of having a table to represent our value functions, we were going to use this generic function approximator where we have a W now, which are some parameters. And when we thought about doing this, we said what we're going to focus on is we're going to focus on function approximations that are differentiable. And the nice thing about differentiable representations is that we can use our data and we can estimate our parameters, and then we can use gradient descent to try to fit our function, to try to represent our Q function or our value function. So I mentioned last time that most of the time we're going to think about trying to quantify the fit of our function compared to the true value as a mean squared error. So we can define our loss J, and we can use gradient descent on that to try to find the parameters W that optimize. And just as a reminder, stochastic gradient descent was useful because then we could just slowly update our parameters as we get more information. And that information now could be in the form of episodes, or it could be individual tuples. When I say a tuple, I generally mean a state, action, reward, next state tuple. And the nice thing is that the expected stochastic gradient descent is the same as the full gradient update. So just to remind ourselves, last time we were talking about linear value function approximators, and that meant that what we're going to do is we're going to have a whole bunch of features to describe our world. So these features, we would input our state is the real state of the world, and we would output our features. And so this could be things like our laser rangefinder for our robot, which told us how far away the walls were in all 180-degree directions. We talked about the fact that that was an aliased version of the world because multiple hallways might look identical. So our value function now is a dot product between those features that we've got out about the world with the weights. Our objective function is, again, the mean squared error, and then we could do this same weight update. And the key hard thing was that we don't know what this is. So this is the true value of a policy. And the problem is we don't know what the true value of a policy is, otherwise we wouldn't have to be doing all of this learning. And so we needed to have different ways to approximate it. And so the two ways we talked about last time was inspired by our work on Monte Carlo or on TD Learning, is we could either plug in the return from a full episode. This is the sum of rewards. Or we could put in a bootstrapped return. So now we're doing bootstrapping, where we look at the reward, the next state, and the value of our next state. And in this case, we're using linear value function approximators for everything, which gave us a really simple form of what the derivative is of this function with respect to w. Basically, it's just our features, times essentially this prediction error. So people sometimes call this as the prediction error, because it's the difference between the value, or right now we're using GT as the true value. Of course, in reality, it's just a sample of the value, but it's the difference between the true value and our estimated value. We want to shrink that difference. So in this case, I've written these equations all for linear value function approximation, but there are some limitations to using linear value function approximation, even though those have been probably the most well studied. So if you have the right set of features, and historically there was a lot of work on figuring out what those right set of features are, they often work really well. And in fact, when we get into, I think I mentioned briefly before, when we start to talk about deep neural networks, you can think of a deep neural network as just a really complicated way to get out features, plus the last layer being a linear combination of those features. For most of the time when we're talking about deep RL with a deep neural network to represent the Q function, that's the type of representation we'll be looking at. So linear value function is often really works very well if you have the right set of features, but is this challenge of what is the right set of features? And there are all sorts of implications about whether or not we're even going to be able to write down the true value function using our set of features, and how easy is it for us to converge to that. So one alternative that we didn't talk so much about last time is to use sort of a really, really rich function approximator class, where we don't have to have a direct representation of the features. And some of those are kernel-based approaches. Has anybody seen like kernel-based approaches before, or like k-nearest neighbor type approaches? Probably if you've taken machine learning, you've heard of k-nearest neighbors. Those are sort of these non-parametric approaches where your representation size tends to grow with the number of data points. And they can be really nice, and they have some actually really nice convergence properties for reinforcement learning. The problem is that the number of data points you need tends to scale with the dimension. So if you have, let's say, those 180 features, the number of points you need to tile that 180-degree space generally scales exponentially with the dimension. So that's not so appealing, both in terms of computational complexity, memory requirements, and sample complexity. So these actually have a lot stronger convergence results compared to linear value function approximators, but they haven't been used in a very widespread way. Yeah. And everyone, just name first, please, just to help me.
Yes.
Yeah.
Sorry, could you repeat again why the exponential behavior happens?
Yeah. The question was, why does the exponential behavior happen in a lot of these sort of kernel-based approximators or non-parametric? The intuition is that if you want to have sort of an accurate representation of your value function, and you're representing it by, say, local points around it, for example, like with a k-nearest neighbor approach, then the number of points you need to have everything be close, like in an epsilon ball, scales with the dimensionality. So basically, you're just gridding the space. So if you think of if you think of sort of, if you want to have any point on this line be close, then you could put a point here and a point here in order to have everything be sort of epsilon close for all points on that line to have a neighbor that's within epsilon distance. If you want to have it in a square, you're going to need 4 points so that everything can be somewhat close to one of the points. And generally, the number of points you need is going to scale exponentially with the dimension. But they are really nice because they can be guaranteed to be averagers, which we talked about really briefly last time, that if you use a linear value function approximator, when you do a Bellman backup, it's not necessarily a contraction operator anymore, which is why you can sometimes blow up as you do more and more backups. The really cool thing about averagers is, sort of by their name, when you use this type of approximation, they're guaranteed to be a non-expansion, which means that when you combine them with a Bellman backup, it's guaranteed to still be a contraction, which is really cool. So that means these sort of approximators are guaranteed to converge compared to a lot of other ones. All right, but they're not going to scale very well, and in practice you don't tend to see them, though there's some really cool work by my colleague Finale Joshi Velez over at Harvard, who's thinking about using these for things like healthcare applications, and how do you sort of generalize from related patients. So they can be useful, but generally don't scale so well. So what we're going to talk about today is thinking about deep neural networks, which also have very flexible representations, but we hope are going to scale a lot better. Now, in general, we're going to have almost no theoretical guarantees for the rest of the day. But in practice, they often work really, really well. So they've become an incredibly useful tool in reinforcement learning and everywhere else, really, in terms of machine learning. So what do we mean by deep neural networks? Well, a number of you guys are experts, but what it generally means in this case is we're just going to think of making a function approximator, which is a composition of a number of functions. So we're going to have our input x, and then we're going to feed it into some function, which is going to take in some weights. So in general, all of these things can be vectors. So you're going to take in some weights and combine them with your x, and then you're going to push them into some function, and then you're going to output something, which is probably going to be also a vector. And then you can push that into another function and throw in some more weights. We're going to do that a whole bunch of times. And then at the very end of that, we can output some y, which you can think of as being like our q. And then we can output that to some loss function, j. So what does that mean here? It means that y is equal to hn of hn minus 1 of dot, 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 dot of h1 of x. And I haven't written all the weights that are going in there, but there's a whole bunch of weights too. And then this is our loss function like before. And this you can think of as like our Q, for example. But these happen a lot in supervised learning, like predicting whether or not something's a cat or not, or an image of a particular object, or for regression. And so why do we want to do this? Well, first of all, it should be clear that as you compose lots of functions, you could represent really complicated functions by adding and subtracting and taking polynomials and all sorts of things you could do by just composing functions together, that this could be a really powerful space of functions you could represent. But the nice reason to write it down like this is that you can do the chain rule to try to do stochastic gradient descent. So how does this work? Well, that means that we can write down that dj, so we really want dj with respect to all these different parameters. And so what we can write down here is we can write down dj of hn and dhn of dwn. And we can do this kind of everywhere. So dj of h2, dh of h2, and dh2 of dw2. So you can use the chain rule to propagate all of this, the gradient of your loss function with respect to w, all the way back down all of these different compositions by writing out the chain rule. And so that's nice because it means that you can take your output signal and then propagate that back in terms of updating all of your weights. Now, I'm going to date myself. So when I first learned about deep neural networks, you had to do this by hand. So as you might imagine, this was a less popular assignment. It's called backpropagation. So you can derive this by hand. And I'll talk in a second about what these type of functions are. You need differentiable functions for H. But I think one of the major innovations that's happened over the, roughly the last 5 to 8 years, is that there's auto differentiation. so that now you don't have to drive all of these gradients by hand. Instead, you can just write down your network parameter and then your network of which includes a bunch of parameters, and then you have software like TensorFlow to do all of the differentiation for you. So I think these sort of tools have made it much, much more practical for people, lots and lots of people, to use deep neural networks, because you can have very, very complicated networks with very, very large neural layers, and there's no sort of handwriting down of what the gradients are. So what are these H functions? Generally, they combine both linear and nonlinear transformations. Basically, they have to be differentiable. So these H need to be differentiable if we're going to use gradient descent to fit them. And so the common choices are either linear, so you can think of Hn is equal to Whn minus 1, or nonlinear, where we can think of Hn is equal to some function Hn minus 1. And if it's nonlinear, we often call this an activation function. Due to time, I'm not going to talk in class much about the connections with neural networks, which is what inside of our brain, which is what's inspiring these sort of artificial neural networks. But inside of the brain, people think of there as being these sort of nonlinear activation functions where if the signal passes a certain threshold, then, for example, a neuron would fire. And so these sort of nonlinear activation functions can be things like sigmoid functions or ReLU. ReLU is particularly popular right now, but so you can choose different combinations of linear functions or nonlinear functions, and as usual, we need a loss function at the end. Typically, we'll use mean squared error. You could also use log likelihood, but we need something that then we can differentiate how close we are at achieving that target in order to update our weights. Yeah, name first.
So this ReLU function is not differentiable, right?
It is differentiable. Like you can take a differential, and it's ended up being a lot more popular than sigmoid recently. Though I feel like it varies.
It's not differentiable at one point.
Yes.
But I don't see how gradient descent is going to work on the part where it's flat.
Well, if it's flat, that's 0. So that ends up just your gradients just disappear. Yeah. So the question is about how for ReLU, there's a lot of it where it's flat, and so if your gradient's 0, then your gradients can vanish there. And in general, actually, we're not going to talk about this at all in class, but there's certainly a problem as you start having very, very deep neural networks, that because of some of these functions, you can sometimes end up sort of having almost no signal going back to the earlier layers. But I'm not going to talk about any of that. We'll talk some about that in sessions. They're good to be aware of, and we're also happy to give other pointers. But yeah, if it's flat, it's okay. You can still just have a 0 derivative. Okay. All right, so why do we want to do this? Well, it's nice we can use this sort of like much more complicated representation. Another thing is that if you have at least one hidden layer, if you have a sufficient number of nodes, nodes you can think of as, if you're not familiar with this, is basically just sort of a sufficiently complicated set of combination of features and functions. This is a universal function approximator, which means that you can represent any function with a deep neural network. So that's really nice. We're not going to have any capacity problems if we use a sufficiently expressive function approximator. And that's important because if you think about what we're doing with linear value function approximators, it was clearly the case sometimes that you might have too limited features and you just wouldn't be able to express the true value function for some states. And what the universal function approximator property is stating is that that will not occur for a deep neural network if it is sufficiently rich. Now, of course, you can always think of doing a linear value function approximator with very, very rich features, and then that becomes equivalent. So given that, what's another benefit? Another benefit is that potentially you can use exponentially less nodes or parameters compared to using a shallow net, which means not as many of those compositions, to represent the same function. And that's pretty elegant, and I'm happy to talk about that offline, or we can talk about it on Piazza. And then the final thing is that you can learn the parameters using stochastic gradient descent. All right, so that's pretty much, deep neural networks in like 5 seconds. We're now going to talk a little bit about convolutional neural networks. And again, this is all going to be a pretty light introduction because you're not going to need to know the details in order to do the homework, except for mostly the fact of understanding that these are sort of very expressive function approximators. So why do we care about convolutional neural networks? Well, they're used very extensively in computer vision. And if we're interested in having robots and other sorts of agents that can interact in the real world, one of our primary sensory modalities is vision. And it's very likely that we're going to want to be able to use similar sorts of input on our robots and our artificial agents. So if you think about this, think about there being an image, this case of Einstein. And there's a whole bunch of different pixels on Einstein, of this picture of Einstein. And let's say it's 1,000 by 1,000. So it's 1,000 by 1,000, X and Y. And so we have 10 to the 6 pixels. So the standard, often called feed-forward deep neural network, you would have all of those pixels, and then they would be going as input to another layer. And you might want to have a bunch of different nodes that are taking input from all of those. And so you can get a huge number of weights. So you might have 10 to the 6 weights for often we think about sort of, I know I haven't given you enough details about this, but often we think of there as being sort of this deep neural network where we have many functions in parallel. So it's not just like a single one, but we might have X going into H1, H2, H3, H4, then all of those would then be going in some complicated way to some other functions. So you can have lots of sort of functions being computed in parallel. And so you can imagine your image goes and you've got one function that computes some aspect of the image and another function that computes some other aspect of the image, and then you're going to combine those in all sorts of complicated ways. So what this is saying is, well, for that very first one, there's maybe going to be a whole bunch of n different functions we're computing of the image. There'd be 10 to the 6 parameters here. So if we have just weights times x, then that would be 10 to the 6 parameters to take in all of that x. That's a lot. And then if we want to do this for doing different types of weights all in parallel, then that's going to be a very, very large number of parameters. And we do have a lot of data often now, but that's still an enormous number of parameters to represent. And it also sort of misses some of the point of what we often think about with vision. So if we think about doing this many times and having lots of hidden units, we can get really an enormous number of parameters. So to avoid sort of this space-time complexity and the fact that we're sort of ignoring the structure of images, convolutional neural networks try to have a particular form of deep neural network that tries to think about the properties of images. So in particular, images often have structure, and the way that our brain processes images also has structure, and there's sort of distinctive features in space and frequency. So when you have a convolutional neural network, we think of there being particular types of operators. So operators, again, here are like our functions, h1 and hn, which I said before could either be linear or nonlinear. And in a convolutional neural network, we're going to have particular structures for those functions that try to sort of think about the properties that we might want to be extracting from images. And kind of the key aspects here is that we're going to do a lot of weight sharing to do parameter reduction. So instead of saying I'm going to have totally different parameters, each taking in all of the pixels, I'm going to end up having sort of local parameters that are identical, and then I apply them to different parts of the image to try to extract, for example, features. Because ultimately, the point of doing this is going to be try to extracting features that we think are going to be useful for either predicting things like whether or not, a face is in an image, or that are going to help us in terms of understanding what the Q function should be. So the key idea, one of the key ideas is to say that we're going to have a filter or a receptive field, which is that we're going to have some hidden unit. So that's going to be a function that's applied to some previous input. At the beginning, that's just going to be a subset of our image. And instead of taking in the whole image, we're just going to take in part. So we're just going to take in a patch. So maybe we're going to take the upper corner, or we're going to take the middle. So it's like we're just going to try to compute some properties of a particular patch of the image. And so then we can imagine taking, it's often called a filter, that little, those set of weights that we're applying to that patch, and we could do that all over the image. And we often call there's a stride, which means sort of how much you move that little patch at each time point. There's also this thing called zero padding, which is how many zeros to add on each input layer, and this determines sort of how helps determine what your output is. So in this case, if you have an input of 28 by 28, and you have a little 5 by 5 patch that you're going to slide over the entire image, then you're going to end up with a 24 by 24 layer next. Because basically you just take this and then you move it over a little bit, and you move it over. And each of those times you're going to take those 25, so this is 5 by 5, so you're going to have 25 input x's, and you're going to dot product them with some weights, and that's going to give you an output. So here in this case, that means we're going to need 25 weights. Okay. So one thing is, instead of having our full x input, we're just going to we're going to direct different parts of the x input to different neurons, which you can think of as just different functions. But the other nice idea here is that we're going to have the same weights for everything. So when we took those weights, we're going to have sort of, you can think of them as trying to extract a feature from that subpatch of the image. For example, whether or not there's an edge. So you can imagine I'm trying to detect whether or not there's something that looks like a horizontal edge in that part of the image, and and that is determined by the weights I'm specifying, and I just move that over my entire image to see whether or not it's present. So now the weights are identical, and you're just moving them over the entire image. And so instead of having 10 to the 6 weights, I'm only having 25 weights, and I'm applying those to the same, just applying them to lots of different parts of the image. Okay, so this is sort of what that would look like. You sort of have this input, you go to the hidden layer, and you're sort of also downsampling the image. Why would you want to do this? Well, we think that often the brain is doing this. It's trying to pick up different sort of features. In fact, a lot of computer vision before deep learning was trying to construct these special sorts of features, things like SIFT features or other features that they think capture sort of important properties of the image that are also maybe invariant to things like translation. Because we also think that, whether I'm looking at the world like this or I move my head slightly, that the features that I see are often going to be identical whether I move to the left or right a little bit. There are particular salient aspects of the world that are going to be relevant for detecting whether or not there's a face and relevant for deciding my value function. So we want to sort of extract features that we think are going to represent this sort of translation invariance. So this means also that rather than just computing, you can do this, you use the same weights all the way across the feature, all across the image, and then you can do this for multiple different types of features. So there's a really nice discussion of this that goes into more depth from 231N, which some of you guys might have taken. And there's a nice animation where they show, okay, imagine you have your input. You can think of this as an image, and then you can apply these different filters on top of it, which you can think of as trying to detect different features. And then you move them around your image and see whether or not that feature is present anywhere. So you can do that with multiple different types of filters. You could think of this as trying to look for whether something's like that or something's, horizontal or vertical, different types of edges. And these give you different features, essentially, that are being extracted. The other really important thing in CNNs is what are known as pooling layers. They're often used as a way to sort of downsample the image. So you can do things like max pooling to detect whether or not a particular feature is present, or take averages or other ways to kind of just down and compress the information that you got in. Just remember, in this case, and in many cases, we're going to start with a really high dimensional input, like X might be an image, and output a scalar, like the Q value. So we're somehow going to have to go from a really high dimensional input and kind of average and slew down until we can get to a low dimensional output. So the final layer is typically fully connected, so we can again think about all of these previous processes as essentially computing some new feature representation. So essentially from here to here, we're kind of computing this new feature representation of the image. And then at the very end, we can take some fully connected layer where it's like doing linear regression and use that to output predictions or scalars. Again, I know either for some of you guys, this is sort of a quick, shallow refresher. For others of you, this is clearly not would be a whirlwind introduction. But we won't be requiring you to know a lot of these details. And again, just go to session if you have some questions, and feel free to reach out to us. Okay, so these type of representations, both deep neural networks and convolutional neural networks, are both used extensively in deep reinforcement learning. So it was around in 2014 where the workshop where David Silver started talking about how we could use these type of approximations for Atari. So why was this surprising? I just sort of want to bring back. So in around 1994, approximately 1994, we had TD backgammon, which used deep neural networks. Well, they used neural networks. I think there was someone deep. And they got like a world-class backgammon player out of that, so that was pretty early on. And then we had the results that were kind of happening around like 1995 to maybe around 1998, which said that function approximation plus offline, off-policy control plus bootstrapping can be bad, can fail to converge. So we talked about this a little last time, that in general, as soon as we start doing this function approximation, even with the linear function approximator, that when you're combining off-policy control, bootstrapping, which means we're doing like TD learning or Q learning, and function approximator, then you can start to have this challenging triad, which often means that we're not guaranteed to converge, and even if we're guaranteed to converge, the solution may not be a good one. So sort of there was this early encouraging success, and then there were these results in sort of the middle of the 90s that were trying to better understand this, that indicated that things could be very bad. And there was sort of some, in addition to the theoretical results, there were sort of these simple test cases these simple cases that went wrong. So it wasn't just sort of in principle this could happen, but there were cases which failed. And so I think for a long time after that, the community was sort of backed away from deep neural networks for a while. People were quite cautious about using them because there were clearly even simple cases where things started to go really badly with function approximation. And theoretically, people could prove that it could go badly. And so there was sort of less attention to it for quite a while. And then there was the rise of deep neural networks in sort of, the mid-2000s, like to now. Deep neural networks became huge, and there was clearly huge success in them for things like vision and other areas. There was a whole bunch of data, there was a whole bunch of compute. They were getting really extraordinary results. And so then perhaps it was natural that like around in like 2014, DeepMind combined them and had some really amazing successes with Atari. And so I think it sort of really changed the story of how people are perceiving using these sort of complicated function approximators and RL, in that yes, it can fail to converge. Yes, things can go really badly, and they do go really badly sometimes in practice. But it is also possible often that despite that, the fact that we don't always fully understand why they always work, that often in practice we can still get pretty good policies out. Now, we often don't know if they're optimal. Often we know they're not optimal because we know that people can play better, but that doesn't mean that they might not be pretty good. And so we sort of saw this resurgence of interest into deep reinforcement learning. Yeah.
I guess, is there anything from your perspective that the deep learning had solved the problems that they had come up with in the mid-90s, or is it just that kind of through increases in computational power and the ability to gather a lot of data, that when it failed, it kind of doesn't matter and we can try some different, try it again, kind of re-put it together and then just keep trying it until it works? I guess my question is, have we actually overcome any of the problems that arose in the late 90s, or is it just that we're just kind of powering through?
Question is, have we sort of fundamentally resolved some of the issues of the late 90s, or are we kind of brute forcing it? I think that some of the issues that were coming up in 1995 through 1998 in terms of convergence, there are some algorithms now that are more true stochastic gradient algorithms that are covered in Chapter 11, so that are guaranteed to converge. They may not be guaranteed to converge to the optimal policy. So there's still a ton of work, I think, to be done to understand function approximator and off-policy control and bootstrapping. I think there's also a couple algorithmic ideas that we're going to see later in this lecture that help the performance kind of avoid some of this convergence problems. So I think people knew about this when they started going into 2013, 2014. And so they tried to think about, well, when might this issue happen and how could we avoid some of that stuff? Like what's causing that? And so at least algorithmically, can we try to make things, people often talk about stability. So can we try to make sure that the deep neural network doesn't seem to start having weights that are going off towards infinity, and at least empirically have sort of more stable performance? Yes.
So with the Atari game specifically, did you avoid the problem of sort of the Dibby triad by having on-policy control, I just don't know enough about things myself, but or was it the case that in fact, in the original experiment, they updated the performance to match the optimal policy sort of in real time, which makes more of an on-policy problem, which avoids the entire issue.
The question is whether or not in the sort of, if I understood correctly, in the Atari case, like, were they changing things to be more on policy or which we know can be much more stable? They are doing deep learning in this case, deep Q learning, and so it can still be very unstable, but they're going to do something about how they do the frequency of updates to the networks to try to make it more stable. And these are great questions. We'll see how it works here. Any others? Okay, cool. So, we'll see an example for Breakout shortly of what they did. So again, right now we're going to be talking about using deep neural networks to represent the value function. We'll talk about using deep neural networks to represent the policy pretty shortly next week. So what are we going to do? We're going to, again, have our weights. We're going to have our same approximators. Now we're going to be using deep neural networks. And in this case, again, just to be clear, we're going to be using a Q function because we're going to want to be able to be doing control. So we're going to be doing control in this case. And so we're going to need to be learning the values of the actions. Just to be clear here, in Atari, it generally doesn't have a really high dimensional action space. It's discrete. It's normally somewhere between like 4 to 18, depends on the game. So it's fairly low dimension, it's discrete and fairly small. So though the state space is enormous because it's pixels, it's images, the action space is pretty small. Okay, so just as a reminder, for Q learning, what we saw is Q learning looks like this for our weights. We have to have the derivative of our function. This is not necessarily going to be linear anymore. But the way we updated our weights was we did this TD backup where we have this target, but we're now going to be taking a max over A over our next state and our action and our weights. Now notice in this equation, all the W's you see are identical on the right-hand side. So we're using the same weights to represent our current value, and we're using our same weights to plug in and get an estimate of our future value, as well as in our derivative. And one thing we're going to see is an alternative to that. Okay, so their idea was we'd really like to be able to use this type of function approximator, these deep function approximators, to do Atari. They picked Atari in part, well, I think at least Demis and I think David both had sort of a joint startup on video games a long time ago. I think it was before David went back to grad school, if I remember correctly. So they're both interested in this. It's clearly, games are often hard for people to learn, so it's a nice sort of demonstration of intellect. And they thought, well, we can get access to this, and there was a paper published, forgetting when, maybe 2011, 2013, talking about Atari games and emulators as being sort of an interesting challenge for RL. So what happens in this case? Well, the state is just going to be the full image. The action is going to be the equivalent of actions of what you could normally do in the game. This is normally somewhere between 4 to 18, approximately 4 to 18 actions. And the reward can be, well, really whatever you want, but you can use the score or some other aspect to as proxy reward. Generally, we're going to think about score. So what's going to happen? Well, they're going to use a particular input state. We've talked before about whether or not a representation is Markov. In these games, you typically need to have velocity. So because you need velocity, you need more than just the current image. So what they chose to do is you need to use 4 previous frames. So this at least allows you to catch for velocity and position of sort of the balls and things like that. It's not always sufficient. Can anybody think of an example where maybe in an Atari game, I don't know how many people played Atari, that might not be sufficient, where, for the last 4 images still might not be sufficient, or the type of game where it might not be sufficient? Yeah.
If you pick up an item in a previous room and then need to use it much later on.
Exactly. The example given by Chris is exactly right. So things like Montezuma's Revenge, things where you often have to get a key, and then you have to grab that key, and then maybe it's visible on the screen, maybe it's not, but maybe it's stored in inventory somewhere. So you have to sort of remember that you have it in order to make the right decision much later, or there might be some information you've seen early on. So there are a lot of games and a lot of tasks where even the last 4 frames will not give you the information you need, but it's not a bad approximation. It's much easier than representing the entire history. So they started with that. So here in this case, there's 18 joystick button positions. May or may not need to use all of them in a particular game. And the reward can be the change in score. Now notice that that can be very helpful or may not be. It depends on the game. So in some games, it takes you a really, really long time to get to anywhere where your score can possibly change. So in that case, you might have a really sparse reward. In other cases, you're getting reward a lot. And so then that's going to be much easier to learn what to do. One of the important things that they did in their paper, this is a Nature paper from 2015, is they use the same architecture and hyperparameters across all games. Now, just to be clear, they're going to then learn different queue functions and different policies for each game. But their point was that they didn't have to use totally different architectures and do totally different hyperparameter tuning for every single game separately in order to get it to work. It really was that the sort of general architecture and setup was sufficient for them to be able to learn to make good decisions for all of the games. I think that was another nice contribution to this paper, is to say, well, we're going to try to get sort of a general algorithm and setup that is going to go much beyond the sort of normal 3 examples that we see in reinforcement learning papers, but it's going to try to do well in all 50 games. Again, each agent is going to learn from scratch in each of the 50 games, but it's going to do so with the same basic parameters, same hyperparameters and same neural network, so same function approximator. All right. And the nice thing is that I think this is actually required by Nature. They released the source code as well, so you can play around with this. So how did they do it? Well, they're going to do value function approximators. So they're representing the Q function. They're going to minimize the mean squared loss by stochastic gradient descent. But we know that this can diverge with value function approximaters. And what are 2 of the problems for this? Well, one is that there's sort of the correlation between samples, which means that if you have S, A, R, S prime, A prime, R prime, it's double prime. If you think about what the value function or the return is for S, and the value function and the return for S prime, are they independent? No, right? In fact, like, you expect them to be highly correlated. They're probably, it depends on the probability of S prime. If this is a deterministic system, the only difference between them will be R. So these are highly correlated. These are not IID samples when we're doing updates. There's a lot of correlations. And also this issue with non-stationary targets. What does that mean? It means that when you're trying to do your supervised learning and train your value function predictor, it's not like you always have the same VPy oracle that's telling you what the true value is. That's changing over time because you're doing Q learning to try to estimate what that is, and your policy is changing. And so it's huge amounts of non-stationarity. So you don't have a stationary target when you're even just trying to fit your function, because it could be constantly changing at each step. So you change your weights, then you change your policy, and then now you're going to change your weights again. And so it's perhaps not surprising that things might be very hard in terms of convergence. So the way that sort of DQN, deep Q learning, addresses these is by experience replay and fixed Q targets. Experience replay, probably a number of you guys have heard about this if you learned about DQN before, is we're just going to store our old data. We've talked about a little bit before of how, like, TD Learning in their standard approach just uses a data point. Now, what I mean by a data point here is really one of these SAR S prime tuples. In the simplest way of TD Learning or Q Learning, you use that once and you throw it away. That's great for data storage. It's not so good for performance. So the idea is that we're just going to store this. We're going to keep around some finite buffer of prior experience, and we're going to basically redo Q Learning updates. So just remember, a Q Learning update here would be looking like this. We would update our weights. That's considered one update. Take a tuple and update the weight. It's like one stochastic gradient descent update. And so you can just sample from your experience, your replay buffer, you compute the target value given your current Q function, and then you do stochastic gradient descent. Now notice here, because your Q function will be changing over time, each time you do your update of the same tuple, you might have a different target value because your Q function has changed for that point. So this is nice because basically it means that you reuse your data. Instead of just using each data point once, you can reuse it, and that can be helpful, and we'll look at that more in a minute. So even though we're treating the target as a scalar, the weights will get updated on the next round, which means our target value changes. And so you can sort of propagate this information, and essentially the main idea is just that we're going to use data more than once, and that's often very helpful. Yes, and name first, please.
My question is, Is this equivalent to keeping more frames in our representation, or is this not?
That's a great question, which is this equivalent to keeping more frames in our representation? It's not, though that's a really interesting question. More frames would be like keeping a more complicated state representation, but you could still just use a state action reward next state tuple once and throw that data away. This is like saying that periodically let's say I went S1, A1, R1, S2, and then I keep going on, and now I'm at like S3, A3, R3, S4. So that's really where I am in the world. I'm now in state 4. It's like I suddenly pretend, oh wait, I'm going to pretend that I'm back in S1, took A1, got R1, and went to S2, and I'm going to update my weights again. And the reason that that update will be different than before is because I've now updated using my second update and my third update, so my Q function in general will be different than before. So it'll cause a different weight update. So even though it's the same data point as before, it's going to cause a different weight update. And in general, one thing we talked about a long time ago is that if you do TD learning to convergence, which means that you go over your data an infinite amount of time, at least in the tabular case, that is equivalent to if you learned an MDP model. You learned the transition dynamics in the reward model, and you just did MDP planning with that. That's what TD learning converges to. Is that if you sort of repeatedly go through your data an infinite amount of time, eventually it'll converge to as if you had learned a model, a dynamics model, and a reward model, and then did planning for that, which is pretty cool. So this is getting us closer to that. But we don't want to do that all the time because there's a computation trade-off, and particularly here because we're in games, there's a direct trade-off between computation and getting more experience. It's actually a really interesting trade-off because in these cases, it's sort of like, should you think more and plan more and use your old data, or should you just gather more experience? But we can talk more about that later. Yeah, question and name first, please.
And so if the experience replay buffer has like a fixed size, just for like clarification of understanding, are those samples like replaced by new samples after a fixed amount of time? Or is there like a specific way to choose what samples to store in the buffer?
Great question, which is, okay, this is presumably going to be a fixed size buffer. And if it is a fixed size buffer, how do you pick what's in it? And is it most recent? And how do you get things out how do you remove items from it? It's a really interesting question. Different people do different things. Normally, it's often the most recent buffer. Can be, for example, the last 1 million samples, which gives you a highlight of how many samples we're going to be talking about. But you can make different choices, and there's interesting questions of what things you should kick out. It also depends if your problem is really non-stationary or not. And what I mean there is like the real world is non-stationary, like your customer base is changing. Yeah.
When we try to strike the right balance between continuing to experience like new data points versus replaying it, do we do something similar to like exploitation versus exploration? Essentially like with random probability, just decide to replay?
The question is about how would we choose between like what, getting new data and how much to replay, et cetera, and could we do that sort of as an exploration-exploitation trade-off? I think this is generally understudied. There's lots of different heuristics people use. Often people have some sort of a fixed ratio of how much they're updating based on the experience replay versus getting putting new samples into there. So generally right now it's sort of a heuristic trade-off. Could certainly imagine trying to optimally figure this out, but that also requires computation. This gets us into the really interesting question of meta-computation and metacognition, of your agent thinking about how to prioritize its own computation, which is a super cool problem, which is what we solve all the time. Okay, so the second thing that DQN does is it first keeps around this old data. The second thing that it does is it has fixed Q targets. So what does that mean? So to improve stability, and what we mean by stability here is that we don't want our weights to explode and go to infinity, which we saw could happen in linear value function. We're going to fix the target weights that are used in the target calculation for multiple updates. So remember here, what I mean by the target calculation here is that reward plus gamma v of s prime. So this itself is a function of w, and we're going to fix the w we use in that value of s prime for several rounds. So instead of always taking whatever the most recent one is, we're just going to fix it for a while. And that's basically like making this more stable, because this in general is an approximation of the oracle of V star. And so you'd really like an oracle to just give this to you every time you reach, an S prime, or you take an action, get a reward, and go to S prime. You'd like an oracle to give you what the true value is. You don't have that, and it could change on every single step because you could be updating the weights. What this is saying is don't do that. keep the weights fixed that you use to compute VES prime for a little while, maybe for 10 steps, maybe for 100 steps. And that just makes the target, the sort of the thing that you're trying to minimize your loss with respect to, more stable. So we're going to have, we still have our single network, but we're just going to maintain two different sets of weights for that network. One is going to be this weights minus. We call it minus because, well, there might be other conventions, but in particular, it's the older set of weights. It's the ones we're not updating right now. And those are the ones that we're using in this target calculation. So those are the ones we're going to use when we want to figure out the value of S prime. And then we have some other W, which is what we're using to update. And so when we compute our target value, we again can sample and experience tuple from the data set, from our experience replay buffer. We compute the target value using our W minus, and then we use stochastic gradient descent to update the network weights. So this is used with minus, this is used with the current one. Yeah.
So, I guess two questions, like intuitively, why does this help? And like, why does it make it more stable? And like, secondly, like, are there any other benefits other than stability from doing this?
Two questions. One is, intuitively, why does this help? Which is a great question. And second of all, beyond the stability, is there any other benefits? So intuitively, why does this help in terms of stability? In terms of stability, it helps because you're basically reducing the noise in your target. If you think back to Monte Carlo, there, instead of using this target, like this bootstrap target, we were using GT. So in Monte Carlo, we used GT, and I told you the nice thing about that was that it was an unbiased estimator of V pi, but the downside was that it was high variance, because you're just summing up the rewards till the end of the episode. And so if things are high variance, when you're trying to regress on them, it's going to be more noisy, and you could be less variance. Imagine that we do something, take the extreme of this. If we want to be, for stability, you could always make your target equal to a constant. You could always make it equal to 0, for example. And if you kept your target fixed forever, you would learn the weights that minimize the error to a constant function. And that would then be stable because you always have the same target value that you're always trying to predict. And eventually you would learn that you should just set your W equal to 0 and that would be fine. So this is just reducing the noise in the target that we're trying to, it's sort of, if you think of this as a supervised learning problem, we have an input X and output Y. The challenge in RL is that our Y is changing. If you make it that so your Y is not changing, it's much easier to fit. And the second is whether or not there's any benefit beyond stability. I think mostly not. This is also sort of reducing how quickly you propagate information because you're using a stale set of weights to represent the value of a state. So you might misestimate the value of a state because you haven't updated it with new information. Yeah.
Is this something you'd want to do for like a linear value function approximator? Is this something that's specific to the deep learning context?
Great question, which is this specific to deep neural networks, or could you use this with linear value function approximator or any value? You could use this with any value function approximator. Yeah, this is not specific. This is really just about stability, and that's true for the experience replay too. Experience replay is just going to propagate information more effectively, and this is just going to make it more stable. So these aren't sort of unique to using a deep neural network. I think they were just more worried about the stability with these really complicated function approximators. Yeah, in the red.
Do you ever update W9 minus at all, or is there a hyperparameter choice?
Great question. So the question is whether or not we ever update W minus. Yes, we do. We can periodically update W minus as well. So in a fixed schedule, say every 50 or every n episodes or every n steps, you update. So like every n, you would set W minus to W.
We know that this works for gradient descent, and you're not using the same kind of structure as gradient descent. You're using the gradient of a different function, subtracting from the value of the different function. How is this supposed to not break gradient descent? Like all those assumptions don't hold it.
The question is, okay, does this really work in terms of gradient descent? This is not. I mean, it's a great question, and these sort of Q-learning are not true gradient descent methods. They're approximations to such. They often do shockingly well given that. Some of the more recent ones, which chapter 11 has a nice discussion of this, sort of the GTDs or gradient temporal difference learning are more true gradient descent algorithms. These are really just approximations. And this, as Tamir's point, this has no guarantees of convergence still. This is hopefully going to help, but we have no guarantees. Yeah.
So in practice, do people have some cyclical pattern and how often they refresh the weight that's used to compute the gradients?
Yeah, this question is, in practice, is there some sort of cyclical pattern of how often you update W minus? Yes. Yeah, there's often particular patterns or it's a hyperparameter choice of how frequently you update this. And it will trade off between propagating information faster and possibly being less stable. So if you make, if n here is 1, then you're back to standard TD learning. If n is infinity, that means you've never updated it. So there's a smooth continuum there.
We know that, like for W, that there are better initializations than just like 0. Something where like you take into account, I guess, like the mean and the variance. Would you initialize W minus just to W, or is there like an even better initialization for W minus?
Yeah, the question is about the impact of how we initialize W can matter, and how do we initialize W minus? Typically, we initialize W minus to be exactly the same as W at the beginning. The choice of it will also affect certainly the early performance. So great questions. Let me keep going because I want to make sure we get to some of the extensions as well. So just to summarize how DQN works, the main 2 innovations it did is it uses experience replay and fixed Q targets. It stores the transition in this sort of replay buffer or replay memory. You sample random mini batches from D. So normally you sample a mini batch instead of a single one. So maybe you sample 10 or whatever other parameter. You do your gradient descent given those. You compute Q-learning using these old targets, and you optimize the mean squared error between the Q network and the Q-learning targets. Use stochastic gradient descent. And something I did not mention on here is that we're typically doing E-greedy exploration. And so you need some schedule here too for how to decay E-greedy. So they were not doing sophisticated exploration in the original paper. So this is what it looks like. You sort of go in, you do multiple different convolutions. They have the images, and they do some fully connected layers, and then they output a Q value for each action. So let me just bring it up for those of you who haven't seen it before. So the nice thing is so you're about to see Breakout, which is an Atari game, and what they do is they show you sort of the performance of what the agent is doing. So remember, the agent's just learning from pixels here how to do this. So it was pretty extraordinary when they showed this in about 2014. And at the beginning, it's learning sort of this policy. You can see it's not doing the right thing very much. And then over time, as it gets more episodes, it's starting to learn to make better decisions about how to do it. And one of the interesting things about it is that, as you'd hope, as it gets more and more data, it learns to make better decisions. But one of the things people like about this a lot is that you can learn to exploit the reward function. So in this case, it figures out that if you really just want me to maximize the expected reward, what the best thing for me to do is to just kind of get a hole through there, and then as soon as I can, start to just bounce around the top line. And so this is one of the things where, if you ask the agent to maximize the reward, it'll learn the right way to maximize the reward given enough data. And so this was really cool that sort of it could discover things that maybe are strategies that people take a little while to learn when they're first learning the game as well. So when they did this, they then showed some pretty amazing performance on a lot of different games. Many games they could do as well as humans. Now to be precise here, oh yeah.
I'm just wondering why while it's playing, the board was like jittering around a lot. Like it wasn't sure of its movements. Like it moved around places often. Like
the paddle.
Yeah.
Yeah. So you might see. I think referring to the fact that the paddle was moving a lot. As the agent's trying to learn, like when we see that, you sort of think, well, why would you jerk a lot? From the agent's perspective, particularly if there's a cost to moving, then it may just be kind of babbling and doing exploration just to see what works. And from our perspective, that's clearly sort of an inexperienced player to do that. That would be a strange thing. But from the agent's perspective, that's completely reasonable. And it's not getting positive or negative reward from that. So it can't distinguish between, just staying stationary versus going left or right. If you put in a cost for movement, that could help.
This might be covered in the paper, but is there a reason why they didn't introduce a pooling layer?
There might be one in there. I don't remember the complete network architecture. The question is whether or not there was a pooling layer in there. I think there might be inside. They have to be going from images all the way up, but they have the complete architecture. That's a good question. So the nice thing that you can see here is that they got sort of human level performance on a number of different Atari games. There's about 50 games up here. Just to be clear here, when they say human level performance, that means asymptotically. So after they have trained their agent. They're not talking about how long it took them or their agent to learn. And as you guys will find out for homework 2, it can be a lot of experience, a lot of time to learn how to do good performance. But nevertheless, there are a lot of cases where that might be reasonable in terms of games. So they did very well on some domains. Some domains they did very poorly. There's been a lot of interest in these sort of games on the bottom end of the tail, which are often known as those hard exploration games. We'll talk a lot more about exploration later on in the course. So what was critical? So I like there's lots of really lovely things about this paper. And one of the really nice things is that they did a nice ablation study for us to sort of understand what were the important features. And if you look at these numbers, I think that it's clear that the really important feature is replay. So this is their performance using a linear network. Deep linear networks seem to not help so much. Using that fixed Q. Fixed Q here means using like a fixed target. Okay, that gets you like a little bit, 3 from 10. You do replay and suddenly you're at 241. So throwing away each data point after you use it once is not a very good thing to do. You want to reuse that data. And then if you combine replay and fixed Q, you do get an improvement over that, but it's really that you get this huge increase, at least in Breakout and some of the other games, by doing replay. Now in some other ones, you start to get a significant improvement as soon as you use a more complicated function approximator. But in general, replay is hugely important, and it just gives us a much better way to use the data. Yeah.
Yeah, judging on this table, it seems like you would want to use replay and fixed Q with the linear model, and that it might be a mistake to be using a deep model here. Do you agree with that takeaway from this table, or?
It's like, well, maybe you could use like linear. Oh, so I guess I should be clear. So this is all, everything on the next 4 were all deep. So they don't have here linear plus replay. But you could certainly imagine trying linear plus replay, and it seems like you might do very well here. It might depend on which features you're using. There's some cool work over the last few years looking also at whether you can combine these two. So we've done some work using a Bayesian last layer, using like Bayesian linear regression, which is useful for uncertainty. Other people have just done linear regression, where the idea is you use sort of a deep neural network up to a certain point, and then you do kind of direct linear regression to fit exactly what the weights are at the final layer. And so that can be much more data efficient, but you still have a complicated representation. All right, so since then, there's been a huge amount of interest in this area. So again, dating myself, reinforcement learning, used to go and give a talk about reinforcement learning, and like 40 people would show up, and most of them you knew, and then it started really changing. I think it was maybe in 2016 when ICML was in New York, and like suddenly there were 400 people in the room for reinforcement learning talks. And then this year at NeurIPS, which is one of the major machine learning conferences, it sold out in like 8 minutes. So there were 8,000 people there, and there was a huge amount of interest in deep learning. And for the deep learning workshop, you sort of have a 2,000 person auditorium. So there's been a huge amount of excitement based on this work, which I think really a huge credit to DeepMind and to the work that David Silver and others have been doing to sort of show that this was possible. Some of the immediate improvements that we're going to go through really quickly here is double DQN, prioritized replay, and dueling DQN. There's been way more papers than that, but these are some of the early really big improvements on top of DQN. So double DQN is kind of like double Q learning, which we covered very briefly at the end of a couple of classes ago. And the thing that we discussed there was this sort of maximization bias, is that the max of estimated state action values can be a biased estimator of the true max. And so we talked really briefly about double Q learning. So in double Q learning, the idea was that we're going to maintain 2 different Q networks. We can select our action using like an E-greedy policy where we average between those Q networks. And then we'll observe a reward in a state. And we basically use one of the Qs as the target for the other. So if, with a 50% probability, we're going to update one network. And we're going to do that by picking the action from the other network. This is to try to separate how we pick our action versus our estimate of the value of that action to deal with this sort of maximization bias issue. And then with 50% other probability, we update Q2 and we pick the next action from the other network. And so this is a pretty small change. It means you have to maintain two different networks or two different sets of weights, and it can be pretty helpful. So if you extend this idea to DQN, you have sort of our current Q network, W to select actions, and this older one to evaluate actions. So you can put this in there to do action selection, and then you can evaluate the value of it with your other networks, other network weights. So it's a fairly small change. It's very similar to what we were doing already for the target network weights. And it turns out that it gives you a huge benefit in many, many cases for the Atari games. So this is something that's generally very useful to do and gives you sort of an immediate significant boost in performance. So, for the equivalent of like a small amount of coding. That's one idea, and that's sort of a direct lift up from sort of, double Q learning. The second thing is prioritize replay. So let's go back to the Mars rover example. So in Mars rover, we had this really small domain. We were talking about tabular settings. There were just 7 states. And we were talking about a policy that just always took action A1, which turned out to mostly go left. So we had this trajectory. We started off in state S3. We took action A1. We got a reward of 0. We went to S2. We stayed in S2 for one round when we did A1, and then eventually went to S1, and then we terminated. So that was this. And the first visit Monte Carlo estimate of V for every state was 1110000. And the TD estimate with alpha equal 1 was this. And that was when we talked about the fact that TD only uses each data point once, and it didn't propagate the information back. So the only update for TD learning was when we reached state S1, we took action 1, we got a reward of 1, and then we terminated. And so we only updated the value of state 1. So now let's imagine that you get to do, now let's think about what your sort of replay buffer would be in this case. You'd have something like this. You'd have S3, A1, 0, S2, S2, A1, 0, S2, S2, A1, 0, S1, S1, A1, 1, terminate. So that's what your replay buffer would look like. So let's say you get to choose 2 replay backups to do. So you have 4 possible replay backups. You can pick the same one twice if you want to. And I'm going to ask you to pick 2 replay backups to do to improve the value function in some way. And I'd like you to think for a second or talk to a neighbor about which of the 2 you should pick and why, and which order you would do them in as well, and whether it makes any difference. Maybe you're like, doesn't matter, you can just pick any of these. You're going to get the same value function no matter what you do. So are there two updates that are particularly good? If so, why, and what order would you do them in? All right, hopefully you had a chance to think about that for a second. First of all, does it matter? So I'm going to first ask you guys the question, vote if you think it matters which ones you pick in terms of the value function you get out. That's right. So it absolutely matters which 2 you pick in terms of the resulting value function. You will not get the same value function no matter which 2 you pick. Now I'll ask for another voting. So I'll ask for which one we should do first. Should we do 4 first? 4 is the last one in our replay buffer. Should we do 3 first? Should we do 2 first? Okay. All right. So 3s have it. Does somebody want to explain why? Yeah.
I think picking 3
helps you kind of back propagate the information you already have on state 1 to state 2. Oh yeah.
Yeah, so what I said is right. So if you pick backup 3, so what's backup 3? It is S2, A1, 0, S1. So if you do the backup, that's 0 plus gamma of V of S prime S1. And this is 1. So that means now you're going to get to back up. And so now your V of S2 is going to be equal to 1. So you get to back up that information. Okay. So I wasn't extremely specific on what like the right thing to do here is, that, but my main thing is that I wanted to emphasize that it makes a big difference, and that it's going to matter in terms of the order. What's the next one we should do? Should we do, raise your hand if we should do 3 again? Raise your hand if we should do 2. Raise your hand if we should do 1. Yep, the ones have it. Someone want to explain why? Yeah, in the back.
And it's the same as the last time. Now you have info on 2, so you want to propagate that back to S1.
That's right. Yeah. So if you wanted to get all the way to the Monte Carlo estimate, what you would want to do here is you'd want to do S3, A1, 0, S2, which would allow your V of S3 to be updated to 1. And at this point, your value function would be exactly the same as the Monte Carlo. So it definitely matters. It matters the order in which you did do it. If you had done S3, A1, 0, S2, your S3 wouldn't have changed. So ordering can make a big difference. So not only do we want to think about like what was being brought up before, but I think to say like what should we be putting in our replay buffer. Not only do we want to think about what should be in our replay buffer, but also what order do we sample them can make a big difference in terms of convergence rates. And in particular, there's some really cool work from a couple years ago looking at this formally of like what the ordering matters. So there was this paper back in 2016 that tried to look at what the optimal order would be. So imagine that you had an oracle that could exactly compute. Now, this is going to be computationally intractable. We're not going to be able to do this in general. But imagine that an oracle could go through and pick and figure out exactly what the right order is. Then what they found out in this case is that for this sort of small chain-like example, you get this exponential improvement in convergence, which is pretty awesome. So what does that mean? The number of updates you need to do until your value function converges to the right thing can be exponentially smaller if you update carefully. And you could have an oracle tell you exactly what tuple to sample, which is super cool. So you could be much, much better. But you can't do that. You're not going to spend all this. It's very computationally expensive or impossible in some cases to figure out exactly what that oracle ordering should be. But it does illustrate that we might want to be careful about the order that we do it in. So their intuition for this was, let's try to prioritize a tuple for replay according to its DQN error. So the DQN error in this case is just our TD learning error. So it's going to be the difference between our current, this is basically our prediction error. So this is our prediction error, almost our prediction error. I'll just call it TD because it's not quite because we were doing it max. So this is like sort of our predicted TD error minus our current. I'm going to say if you have a really, really big error, then we're going to prioritize updating that more. And you update this quantity at every update. You set it for new tuples to be 0. And one method, they have 2 different methods for trying to do this sort of prioritization. But one method basically takes these priorities, raises them to some power alpha, and then normalizes. And then that's the probability of selecting that tuple. So you prioritize more things that are weights. Yeah.
Doesn't freezing
Name first, please.
Doesn't freezing the old weights work counter to propagating back the information though? Because like if you froze the old weights in the example we were just going through, after you like propagated the one back once, you wouldn't be able to do it anymore because your value would still be 0.
That makes a great point, which is if you were fixing your W minus, then if you were looking at our case that we had before, then you wouldn't be able to continue propagating that back because you wouldn't have updated yet. Yeah, that's exactly right. So there's going to be this tension between when you fix things versus sort of propagating information back. And it's a tension that one has to sort of figure out. There's not necessarily principled ways for exactly what the right schedule is to do that, but it's a hyperparameter to do.
So why does ordering matter then if you're fixing it so you're not changing? Like then it wouldn't matter what order we sampled those previous ones, right?
Okay, so asynchronous, so does ordering matter at all in that case? It still matters because we're still going to be doing replay over, the weights will be changing during the time period of which we'll be replaying over that buffer. So that buffer could be like 1 million, and you might update your weights like every 50 steps or something like that. So there's still going to be a whole bunch of data points in your replay buffer that it's useful to think about now that your weights have changed. What ordering do you want to go through those? It's a great question. Okay, so one method is this. Let me just to clarify. If we set alpha equal to 0, what's the rule for selecting among existing tuples? So pi is our sort of basically our DQN error. If we set alpha equal to 0, uniform. That's right. Yeah. So this sort of trades off between uniform, no prioritization, to completely picking the one that, like if alpha is infinity, then that's going to be picking the one with the highest DQN error. So it's a trade-off. It's a stochastic. All right. So then they combine this with sort of, the reason I'm picking these three order do is they all sort of layer on top of each other. So prioritized replay versus, I think this is prioritized replay plus double DQN versus just double DQN. Most of the time, this is 0 would be they're both the same. Underneath means flat vanilla double DQN is better. Above means that prioritized replay is better. Most of the time, prioritized replay is better. Again, there's some hyperparameters here to play with, but most of the time this is useful. And it's certainly useful to think about, where order might matter. All right, we don't have very much time left, so I'm just going to do short through this just so you're aware of it. One of the best papers from ICML 2016 was dueling. The idea is that if you want to make decisions in the world, there might be some states that are better or worse, and they're just going to have higher value or lower value, but that what you really want to be able to do is figure out what the right action is to do in a particular state. And so that what you want to sort of understand is this advantage function. You want to know how much better or worse taking a particular action is versus following the current policy. That really, I don't care about estimating the value of a state, I care about being able to understand which of the actions has the better value. So we're looking at this advantage function. So what they do to do this is that in contrast to DQN, where you output all of the Qs, they're going to separate and they're going to first estimate the value of a state, and they're going to estimate this advantage function, which is Q of S A1 minus V of S. Q of S A2 minus V of S. So I'm just going to separate it. It's an architecture choice. And then they're going to recombine these for the Q. And they're going to argue this is going to help us sort of focus on the signal that we care about, which is being able to accurately estimate which action is better or worse. There's interesting questions about whether or not this is identifiable. I don't have enough time to go into these today. It is not identifiable. I'm happy to talk about all of that offline. The reason this is important is it just forces one to make some sort of default assumptions about specifying the advantage functions. Empirically, it's often super helpful. So again, compared to double DQN with prioritized replay, which we just saw, which was already better than double DQN, which is also better than DQN, this again gives you another performance gain, substantial one. And so basically these are sort of three different ones that came up within the sort of 2 years after DQN that started making some really big performance gains compared to just doing completely vanilla DQN. For homework 2, you're going to be implementing DQN, not the other ones, though you're welcome to implement some of the other ones. But it's just good to be aware of those are some of sort of the major initial improvements to getting substantially better performance on Atari. I'll leave these up. We're almost out of time. Feel free to look at the last couple slides of this for some practical tips that came from John Schulman. John Schulman was a PhD student at Berkeley that is now one of the heads of OpenAI. Just one thing that I will make sure to highlight, it can be super tempting to try to start by implementing Q-learning directly on Atari. I highly encourage you to first go through sort of the order of the assignment and do it with the linear case, make sure your Q-learning is totally working before you deploy on Atari. Even with the smaller games like Pong, which we're working on, it is enormously time consuming. And so in terms of just understanding and debugging, it's way better to make sure that you know your Q-learning method is working before you wait 12 hours to see whether or not, it didn't learn anything on Pong. So there's a reason for why we sort of build up the way we do in the assignment. Just a few other practical tips. Feel free to look at those. And then we'll meet more on Thursday. Thanks.